Generating an image this intricate requires the leading models in the field, systems like Midjourney V8, DALL 3, and Stable Diffusion. But building a picture like that from scratch is a massive mathematical challenge. To a computer, an image is a grid of numbers representing pixel colors. Attempting to calculate a coherent scene from a blank slate involves an unmanageable number of variables. Researchers solved this by applying the physical principles of thermodynamics. In physics, if you drop red dye into a beaker of water, the particles spread out until the system reaches equilibrium, a uniform, noisy pink. This decay into noise is highly predictable. If a neural network learns the mathematical laws of how structure dissolves into static, it can reverse that process to pull highly detailed structure out of the noise. This illustrates forward diffusion. The AI takes real images, like this dog, adding Gaussian noise step by step until it becomes pure static. The reverse arrows represent reverse diffusion. A neural network predicts the added noise and subtracts it, peeling back the static to reconstruct the image. Reversing noise on millions of high-resolution pixels is computationally expensive. To speed this up, an autoencoder compresses the image into a latent space, a smaller, mathematically dense representation. This breakthrough, called latent diffusion, allows these massive reverse physics calculations to happen fast enough to run on consumer hardware. If the model starts with a block of random noise, how does it know which specific image to sculpt when you type a prompt? It relies on CLIP, or contrastive language image pre-training. This system studied hundreds of millions of image-text pairs to learn the mathematical connections between human descriptions and visual data embeddings. Through conditional guidance, the AI uses CLIP text embeddings as a map. It references the prompt to identify exactly which patterns of noise to remove from the static. The system takes a block of random noise and carefully chisels away the static until it satisfies the conditions of your words. True mastery of these models requires acting as a director who manipulates the underlying math rather than just typing a simple prompt. Negative prompts provide this control by telling the AI exactly what to keep out of the image, such as anatomical errors or blurriness. The model handles this through classifier-free guidance, or CFG. It generates two separate predictions, one positive and one negative, and compares them. The CFG scale acts as a multiplier, pushing the final image away from the negative prediction and toward the positive one. Through CFG and negative weights, users mathematically force the model to abandon bad structural choices before the image even forms. While text and CFG control style and concept, they struggle to dictate exact pixel placement or physical composition. ControlNet solves this by allowing users to feed the AI visual blueprints, such as a stick figure pose or structural edges, to physically constrain the diffusion process. With ControlNet active, the AI strictly fills in textures and lighting based on the human's exact blueprint, rather than guessing the layout. Text-to-image AI functions as a physics-inspired engine of reverse entropy. By understanding latent space, CFG, and ControlNet, users sculpt